Hello, and welcome back to the course on Physics for Engineers. We are still on the chapter on magnetostatics. So before we proceed with this lesson, let us first review some concepts. So in the previous lesson, we have defined what is a magnetic field. It's actually created by moving charges such as a current. So in the first lesson, first chapter of this course, you have discussed about vectors, wherein when you went to vector operations, specifically the cross product between two vectors, you have learned about the right hand rule. So right hand rule means you use your right hand for crossing vectors. So if the first vector A is your pointing finger, and the second vector B is your middle finger, then your thumb, the direction of your thumb, is the cross product between vector A and vector B. So right hand rule means you use your right hand, not your left hand. So for this lesson, we will be talking about uh, the different sources of magnetic field. So we will be talking about the magnetic field of moving charges, the field of current carrying conductors, and lastly, the magnetic field of current loops. So let's first go or discuss the magnetic field of a moving charge. So suppose you have a moving charge Q. Let's assume it's positive. And then it's moving towards the positive x-axis with velocity v. So what is the magnetic field, say a distance r from the charge Q? So the magnetic field is given by this equation. So it's mu naught over 4 pi Q, the magnitude of the charge, or the charge rather, V cross R over R cube. So this is the vector magnetic fields. And take note, this is now the cross product operation. So this is the field, a distance r from a moving charge Q. Mu naught here is just a constant. It's equal to 4 pi times 10 to the negative 7 Tesla meter per ampere. And the SI unit of magnetic field is the unit called Tesla with the symbol T. So of course this symbol is named after Nikolai Tesla. So the magnetic field direction can be easily obtained by just taking the cross product of V and R. So V cross R, so our V, for example, this is our V, and this is our R. So V cross R, ang V is in the I hat direction, ang R is in this case in the J hat direction, positive y-axis. So I hat cross J hat is equal to K hat. So it's out of the page. So the magnetic field here on any point actually on this top, on this side, will be out of the page actually. So V cross R of that, so V cross R of this is always out of the page. Now, if you have a point below, then if you take the V cross R, so if this is your V, sorry, if this is your, rather like that. So if this is your V, and this is your R is now pointing downwards. So R is from the charge to the point where you want to find the magnetic field. So V cross R will get you this one. So right hand rule again. The pointing finger is your V, the middle finger is your R, V cross R, and this is the direction. The thumb, the direction of the thumb is your the direction of the V cross R, which is essentially the direction of the magnetic field B. So in this case, uh, V cross R here, this is my V, my R is downward, so my magnetic field is into the page. Or it's easier to look at this one. If this is V, this is R, then this is V cross R, this one. So into the page. Take note, it's different from this one. So this is V, this is R, V cross R. So the direction of the magnetic field is out of the page. So this one, towards you. So this is, if you have a point symbol, this is basically a vector that's pointing towards you. You are seeing the tip of the arrow of the vector. So this one, the tip. If you are seeing this one, an X, it means you are looking at the bottom of the vector. Okay. So the magnetic field actually curls around the path of the moving charge. So if this is the path of the moving charge, then the magnetic field is actually curling. So it's still right-hand rule. If this is the direction of the path of the moving charge, then the direction of the magnetic field is actually this one, the curl. When you curl your fingers around your thumb, that's the direction of a magnetic field. So this magnetic field actually points points out, and then it curls around and then goes inside. So if we take another view of this, so for example, I rotate my axis. So from this axis, I rotate it in such a way that the x-axis now is going towards you, and the z-axis is now this one. So I'm just rotating from this axis here. I'm rotating it like that, such that the positive x-axis is now going towards you out of the page, and the positive z-axis is that one. So in that case, the magnetic field V cross R. So you have V cross R. The V is your fingers, and then the R is your ano. So like this. So V is going towards you. This is your R. So this is the direction for magnetic field at this point. So it's going to the positive Z axis. So you take the V cross R at every point, and you will notice that the magnetic field actually is just curling around the path of the moving charge. So if the moving charge is moving in this direction, then the magnetic field is curling. It curls around the path of the moving charge. Okay. So let's now have the magnetic field of a current carrying conductor. So suppose you now have a current, a wire carrying a current I. So in the same manner, the magnetic field at a certain point is given by this equation. You just need to take the cross product between the current and the R, the position vector. So I cross R. So if this is I and this is R, then I cross R is this one, uh, out of the page. So we term this equation as the Biot-Savart law. Bio, so it's not pronounced as Biot, it's Bio. Biot-Savart law. In special cases where there's a constant current and you have a very long current carrying wire, straight and very long current carrying wire, then the magnetic field, a perpendicular distance r from a very long and straight current carrying conductor will just be this one, mu naught I over 2 pi r. So the Biot-Savart law equation will just be reduced to this one. If you have a very long and straight current carrying conductor, so the magnetic field still curls around the current. So if this is the direction of the current, my thumb is the direction of the current, the magnetic field will curl around the current. So the magnetic field here is going out, and it will curl around, turn, and it will go inside in the lower part. So it will curl around. So it's going out of the page and then into the page. So that one, it's curling around the current. If the direction of the current is this one, my thumb, then the magnetic field is this one, curling around my current. So in another view, if I rotate this in such a way that the positive x-axis is now pointing towards you, like that, then the current is moving through the positive x-axis, which is going towards you, and the magnetic field is curling around the current. Okay. So this is the magnetic field pattern for two parallel wires with the same current. And this actually signifies attraction. So if you will notice our current carrying wires, the copper wires that we are using for our electrical devices are actually composed of multiple wires banded together. So the magnetic field pattern between those wires looks similar to like this, and that will actually correspond to an attraction. So if two of the fibers or four of the fibers of your wire contains a current, they will actually stick together. So there will be attraction in between them. On the other hand, if you have two current carrying wires with opposite current, so one current is going this way and the other current is going that way, then that will create a magnetic field pattern looking like this, and that will correspond to a repulsive force between the two wires. Okay, let's now go to the last source of magnetic field, a current loop. So basically, if you have a current loop, it's just basically a current carrying conductor, say a current carrying wire, and it's now forming a closed loop, a closed figure. So if you now have a circular loop carrying a current I with radius A, from the law of B sub R, you can get the magnetic field of a circular current loop. And at the center of the circular current loop, the magnetic field is just mu naught Ni over 2A, where N is the number of turns of the loop. So how many turns, how many windings does your circular loop have? And A is the radius of the loop. So this is just the magnetic field at the center of the loop. So we'll only consider at the center, magnetic field at the center of a loop. So in this case, the magnetic field actually is out of the page. So similar to magnetic field curling around the current, then a current also curls around the magnetic field. So that's a vice versa relationship. So if this is my direction of the current, my thumb, this is the direction of the magnetic field. If this is the direction of my magnetic field, then this is the direction of my current. So in this case, the current is in this direction, it's counterclockwise. Therefore, the direction of the magnetic field is in this direction, out of the page. If in the event that the direction of the current is clockwise, then the direction of the magnetic field is into the page. So that one. Let's also consider a special kind of current loop called a solenoid. A solenoid is basically just a current loop with length L. So you may have seen a solenoid before. It's basically a coil of wire with a certain length L. So in this case, the magnetic field of a solenoid is just mu naught Ni over L, where again N is the length, number of turns. How many turns does your solenoid have? And L, the length of the solenoid. So this is the field inside the solenoid with N turns and length L. So the field or the magnetic field inside the solenoid is actually quite uniform. So even if it's not at the center, so anywhere inside the solenoid, the magnetic field is given by this one, mu naught Ni over L. But outside of the solenoid, it now becomes the magnetic field of a dipole. Since basically, when there's current in your solenoid, it becomes a magnet. One end becomes a north pole, and the other end becomes a south pole. And near the outside vicinity of the solenoid, the magnetic field is actually 0. So let's now have an example. So let's first have a moving charge. So a charge is moving towards the positive y-axis, so that one. So find the magnetic field at the point along the positive x-axis at x is equal to 2 nanometers. So we are asked to find the magnetic field at this point due to the moving charge, which is moving upward. So by virtue of right-hand rule, we can actually find the direction of the magnetic field. So this is the direction of the moving path of the moving charge. So meaning the magnetic field will curl around in this direction. So it will come out, it will be out of the page in this side, but it will be into the page in this side. So into the page, that's actually the negative z axis. So the negative z axis, because the positive z axis is out of the page. So that since it's going into the page, that's the negative z axis. So the magnetic field at this point will actually have a direction directed into the page or the negative z axis. Okay, so that's our r, the vector r. This is our vector b. And by virtue of the right hand rule, v cross r. So this is my v, this is my r, my middle finger, my v is my pointing finger. So v cross r equals this one, v cross r. So that's the direction into the page, the direction of my magnetic field. Okay. So let's try to formulate this in vector terms. So our velocity is only purely y component. There's no x, there's no z component. Meaning the 200 meter per second magnitude, that component is actually the y component. So 200 meter per second j hat. So our r here is purely x component. There's no y component, there's no z component. It's purely x component. So our r is basically 2 nanometer I hat, or the nanometer is times 10 to the negative 9. Nano means times 10 to the negative 9. And of course, the magnitude is 2 times 10 to the negative 9. Okay, so we use this formula, mu naught q v cross r, mu naught over 4 pi q v cross r over r cubed. So this is mu naught, 4 pi times 10 to the negative 7 Tesla meter per ampere over 4 pi, so 4 pi will cancel actually. So our Q is 1 nanocoulomb. So the charge of the magnitude or the charge in this case is 1 nanocoulomb. Nano means 10 to the negative 9. So 1 times 10 to the negative 9 coulomb. And then our velocity is 200 meter per second j hat. Our R is 2 times 10 to the negative 9, 2 nanometers I hat. And then the magnitude of R is 2 nanometers, or 2 times 10 to the negative 9 meters, and then you take the cube because it's R cube here. So combine all of those units, and that unit, all of those units will make up the unit called Tesla, the unit for magnetic field. So in this case, the magnetic field is 5 times 10 to the negative 3 Teslas, negative k hat, because j hat cross I hat is negative k hat. Just as we predicted, it's going to the negative z axis. So the negative k hat is the negative z axis. So the magnetic field is 5 times 10 to the 3 Tesla. The magnitude, the direction is negative z hat, or into the page. Okay, let's consider a current carrying conductor. So let's try to find the magnetic field between two wires. So two wires carry currents of 1 ampere but in opposite directions. So this will actually result in a repulsion. So the two wires are separated by a distance of 3 centimeters. Find the magnetic field at a point P located 2 centimeters to the right of wire A. So there's point P here, and you are asked to find the magnetic field at this point. So the magnetic field at this point will now be a superposition of the magnetic field due to wire A and the magnetic field due to wire B. So you just need to add those two magnetic fields. So in this case, by virtue of right-hand rule, the current in wire A is out of the page, meaning it will curl around in a counterclockwise direction. So counterclockwise direction meaning at point P, the direction of the magnetic field due to wire A is upward. Now, for wire B, it's into the page. So meaning the magnetic field will curl around wire B in a clockwise manner. So clockwise manner meaning at point P, the direction of the magnetic field at point due to wire B will also be upward because it's a clockwise manner. In wire A, it's a counterclockwise manner, but it just so happened that at point P, both of their magnetic fields are directed upwards. Okay, since we have defined the axis here, the positive x-axis is to the right, the positive y-axis to the left, so meaning all of these two magnetic fields are purely y components. So we can just add them directly and say that their directions is along the positive y-axis. Okay. So the magnetic field now at point P will be due to wire A, magnetic field of wire A plus magnetic field of wire B. So for wire A, it's mu naught I over 2 pi RA. RA is the distance from wire A to point P. That distance, that's the R for wire A. Plus mu naught I over 2 pi RB. So this one. So RB in this case, if this is 3 centimeters and this is 2 centimeters, therefore this is 1 centimeters. But you need to convert that into meters. So that it will not be a long solution. We factor out the common factors since they have the same amount of current I equal to 1 ampere. So we take out mu naught I over 2 pi, factor out mu naught I over 2 pi, and then you will have 1 over RA plus 1 over RB. So substitute the values. That's mu naught. And then 1 over RA. RA is 2 centimeters, or in meters, that's 0.02 meters. RB is 1 centimeter, or in meters, it's 0.01 meters. So the final unit will be the SI unit Tesla. So you will get the magnetic field is 3 times 10 to the negative 5 Tesla, and its direction will be along the positive y axis. Since both of these directions are along the positive y axis. So of course, you can take the vector approach of this. You will still get the same result. So in terms of vectors, if you use the vector approach, you will get 3.3 times 10 to the negative 5 j hat. So this is just the vector form, this is just the magnitude and direction form, but they are just both equally the same. Okay, Let's have another example for a current loop and a solenoid. So let's try to find the current the magnetic field of a current loop versus a solenoid. So this is just the main difference of a current loop and a solenoid. A current loop is basically just a loop of a wire. It has no specific length. But if your loop now has a certain current loop now has a certain length, it now becomes what we call a solenoid. So basically, a solenoid is a current loop. So a circular current loop has 1,000 turns and radius of 5 centimeters. If a current of 1 ampere flows through the loop, so in this one, there's a 1 ampere current flowing through 1,000 turns of this loop. What is the magnetic field at the center of the loop? And what is the magnetic field inside the solenoid with the same number of turns, so still 1,000 turns, and then same radius and same current. So radius is 5 centimeter, current is 1 ampere, but it now has a length of also 5 centimeters. So for the first problem, so for the formula, they both have different formulas for magnetic field. And again, their magnetic field formulas came from the law of Biot-Savart. That's our mother equation, the law of Biot-Savart or the Biot-Savart equation. So for a current loop, it's mu naught Ni over 2A. So this is the field at the center. Take note, this is only at the center of the loop. Not on any point, but at the center of the loop. So substitute mu naught. The number of turns is 1,000. Current is 1 ampere. The radius is 5 centimeter. Convert that to meters, 0.05. The final unit is Tesla. So you will get 0.136 Tesla. So that is for the current loop. For the solenoid, it has a different formula, mu naught Ni over L. So the radius actually doesn't matter for a solenoid. So the radius doesn't actually matter for a solenoid, as long as the radius is not large enough as compared to the length. So for a solenoid, the length is very much larger than the radius. It's inverse for a current loop. For a current loop, the radius is very much greater than the length of the current loop. So that's their difference. So very large radius ang current loop, very large length ang solenoid. So in this case, you will have 1,000 turns, 1 ampere, 5 centimeter length. This is the length of the solenoid. So 0.05 meters. And you will get 0.068 Tesla. And it just so happened that in this case, the magnetic field inside the solenoid is 1/2 of the magnetic field at the center of this current loop here. Okay. So that is the end of this lesson. So for the next lesson, we will be talking about some generalizations on how we obtain the magnetic fields, or basically an alternate way, another way to solve the magnetic field of current carrying materials or moving charges, and that is by virtue of Ampere's law. So Ampere's law is basically the analog of Gauss' law in electrostatics. So I will see you again in the next lesson. Bye bye.